Hi all, this is Mr. Yeager for Honors Chem, and we are on to our last part of stoichiometry, which is limiting reactants. So this is probably considered the toughest part of the unit, okay? So here we go with it. I mean, we basically have to just add, as always, one more step to what we're already doing. So first off, what do we mean by limiting reactant? Let's talk about a couple terms you're going to see in these problems, okay? Limiting reactant is a reactant that will run out first in the chemical reaction, okay? I mean, it's just like if you did any sort of baking or, I mean, you're trying to create something and you're going, oh my gosh, how did I not have enough, nails? How do I not have enough sugar, all right? Clearly that will limit then how much you can make, all right? I want to make a bacon, egg, and cheese sandwich in the morning, all right? But the problem is if I don't have eggs, I'm not going to have a single bacon, egg, and cheese sandwich. I can make it bacon cheese, but there will be no egg in it. So what is the limiting reactant? The thing that you are out of, or obviously in these chemical reactions we're saying that we have it, but it will react and run out first based on the amount you have. This is a hugely important factor to understand because that limiting reactant then determines how much product is formed, okay? And that means we then use that reactant the rest of the way. In every problem we've had basically so far, it said, oxygen reacts with excess hydrogen, meaning, you're only given one number. You're given the amount of oxygen, so there's no reason for you to worry about the hydrogen because it says there's excess hydrogen. So we will be able to use all of that oxygen because we have an unlimited supply of hydrogen in the problem. In these problems now, you're going to see is it'll say you have this much oxygen and this much hydrogen. Figure out how much water forms. The thing is you can't just use both. They don't, like you could go ahead and solve for both, but only one is correct in the end. And I mean some people actually do it that way where they go through and the reactant that produces less clearly must be the limiting reactant because it can't produce as much as the excess reactant. Okay? So the limiting reactant runs out first and is what we use in our stoichiometry. From there, excess reactant, we often will go back and say, well, how much excess reactant is left over? The excess reactant, as the name implies, is the one you already have too much of. The reaction would keep going if the limiting reactant didn't stop it. Okay, the excess reactant actually would still be there, and it's one of the things in chemistry at the end of a lab we actually need to try to isolate or we need to filter out that excess reactant because we don't want to have incorrect results. Okay, so again, I just have another example here. Obviously, all the supply chain issues this year. I mean, that's the idea of limiting reactants. There's limited sources. There's limited transportation. It's what's the limiting factor, basically, that can't result in the end product. So, the steps for limiting reactants. I'm going to go through them, and then I'm going to try a couple problems with you. So, steps for limiting reactants. You're going to have to, again, write and balance that chemical equation. So, that's kind of standard. Write and balance the chemical equation. Since you will be given two reactant masses, we need to find the moles of each reactant first. All right? So you will be given, like I say, mass of hydrogen and mass of oxygen. We need to convert that into moles. From there, there's lots of different ways to kind of figure out the limiting reactant here. Okay, I'm going to kind of share each one with you, and you might even find some other ways to do it. That's fine. All right, but these are kind of some of the ways that I can recommend to go through it. The first way is to compare the mole ratio. Compare the mole ratio from the chemical equation, so that mole ratio, to the mole ratio from your compared to the mole ratio of the compounds that you put together in the problem itself. So in other words, you find the moles from step number 2, and we'll find out what that ratio is and see how it's matching up to the chemical reaction mole ratio. What we will see there, and I'll show this in one of my problems, is the idea of if you can notice that, hey, according to the equation, I need 2 times moles as the other one, but then I look at my mole values and I see that I'm less than 2 moles of the other one, I can determine which one is the limiting reactant. So I can compare the mole ratio from the chemical equation to the one that we calculate using step number 2, finding the number of moles of each of the reactants. So that's one method. Some people really don't like that method. It is technically the fastest method because you can kind of, but you got to be able to have number sense and kind of go, I can see the difference in the ratios and I know which one is messing it up now, okay? The more common, probably the most common way to do it is this way, part B. Calculate the number of moles of one of the products that can be made from each reacting using stoichiometry. So in other words, use your moles of oxygen and figure out the amount of water that would be produced. Use your moles of hydrogen separately and figure out the number of the moles of water that can be produced. Whichever reactant produces less is the limiting reactant. So whichever one that you do that. So it does involve two stoichiometry quick little conversions, okay? And that's why it's technically a little slower than A, comparing the ratios. But B is probably your safest bet to do it, okay? In terms of going, okay, I just don't see the ratio, don't bother with that. Just solve for moles of water, use each one, do that one extra step using the mole ratio, and whichever one produces less is the limiting reactant. Another one that I just throw out here, I don't use this method almost at all. I would use method A and B. But method C, you can calculate the number of moles of the other reactant using stoichiometry. And then compare how much you actually have to how much it says that you will need to have. And whichever one basically is saying that you don't have enough of, that must be your limiting reactant. Okay? So I don't plan on showing that method. That would be something that if students are like, I'm not getting any of these, it's no more difficult than B. I mean, B I feel like would be easier to do, actually. I think C is more complicated. But that is another method we can do it. Okay? In all cases, the limiting reactant is then used in all stoichiometry calculations for theoretical yields of products. So you might see a problem where I combine percent yield with limiting reactant. How do I know? I give you the mass of both of the reactants and I say, what will the percent yield be for this product? I need to figure out which one will actually give me the true value, the true theoretical value based on which one is the limiting reactant. And there's more, we're not done. One last step that we usually take with these is we often will ask how much reactant will be left, how much of the excess reactant will be left. One will be gone. Limiting reactant goes away, it's zero, it's all gone. But there will be some excess reactant. Some of it reacts, some of it does not, okay? So we need to usually figure that out. Basically, it's just yet another stoichiometry problem. We do mass-to-mass stoichiometry, or if you're in moles already, moles-to-mass stoichiometry, from the limiting reactant to the excess reactant. So we start with the limiting. Limiting is what we start with. This will show you how much is used in the reaction. So when you solve for this is with common error, when you do mass-to-mass from limiting to excess, that determines how much you've used, not how much is left. So that'll show you how much is used, and then all you do is subtract the initial amount of excess reactant given to you by the amount used, and that's how much is left. Okay? So that is another problem I will show in a moment. Okay? But again, the limiting reactant is very powerful in the sense it will determine what happens throughout the whole reaction. Okay? So that's why it's so important to identify it. All right? So that's basically what we got with that part. After this, you're done! We've done it. We've checked everything off. Yay! Okay. All right. So let's try a couple problems here. Okay? I might have to rewrite this reaction at the top here. We have iron plus H2O producing this black oxide of iron, Fe3O4, okay, plus H2O. No, H2O, sorry about that. I was like, wait a minute, plus H2, okay? So if I balance this reaction on out, step one, so there's my chemical reaction. It says when 36 grams of H2O is mixed with 167 grams of iron, which is the limiting reactant. Well, first step, let's balance our chemical equation. All right? If I balance this out, I could sit here and be like, I have 1 Fe, I have 3, so 3 goes right there. Okay? I then have 2 hydrogens, that looks good so far, but 1 oxygen, 4, so I need to put a 4 right there. Now I have 8, so I need to put a 4 over there. So there's my balanced chemical equation, 3, 4, 1, 4. Okay. All right. So I have 36 grams of H2O and 167 grams of hydrogen. Which is the limiting reactant? The first thing that you absolutely never, ever, 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 ever do, never, don't do it, please don't do it, okay, is just go, well, I have less water, so that means that must be my limiting reactant. The mass does not determine what the limiting reactant is, all right? Of course, could you get lucky and go ahead and be like, hey, I'm going to pick H2O because it has less mass, and you end up actually being correct? Of course, okay? But this is not, like, it shouldn't be a 50-50 chance thing of, I'll just go with this one and see if I'm right, okay? And obviously in these problems you often have to prove which one's the limiting reactant. You can't, like, if you just said it has less mass, that is not the answer to it, okay? That will never, ever be accepted as the answer with it, all right? We should be getting these correct, you know, hopefully 100% of the time, right? So, if I try to start working through it, what do I do first? My first step is to convert both of these into moles. Both of them into moles, okay? So, if I do that, I have 36 grams of water, and that would be 1 mole of water and 18 grams. So this actually comes out to a nice 2.00 moles of water. Okay? 167 grams of iron. Nice thing is it's just the element by itself. And I believe that's 55.85. Yep, 55.85 grams, 1 mole. And that equals 2.99 moles of iron. Okay. So now I see that I have 2 moles of water and 2.99 moles of iron. Again, it has nothing to do with which one has less moles. It goes now to the ratio. It goes now to the ratio itself. All right? And so this is what I mean by we can try to look at this ratio a little bit. Okay? We can look at what we got here. I have a 3 Fe to 4 mole ratio of H2O. My one down here is 2.99 Fe to 2 moles of H2O. If I look at that, what this is saying in the top part, in the chemical reaction, I mean, this would be kind of one of the first things just to look at. Now, again, you might have to do a little bit more than this, but this reaction is saying I need more moles of water than I do of iron to complete the reaction, okay, by a 4-to-3 ratio, which again is not that much, but it's saying I need more moles of water compared to less moles of iron. And I mean 2.99, that's basically 3 moles. So if this is 3 moles, in order to completely react, this Fe, I need 4 moles of water. But how much water do I actually have? Only 2. So that's the idea of kind of looking at the ratio and going, oh, well, because of the ratio showing me that it has less moles with it, okay, it's not meeting the threshold, H2O must be my limiting reactant, which I often just abbreviate LR. Okay? So that's one way. If you're like, what did he just do? I don't understand any of that. Okay? Again, we can look at the ratio and figure that part out. I used to do this thing where like I would subtract, I would go ahead and divide the 2 numbers, and if the number was larger in the reaction compared to this, I don't do that anymore. Okay? But maybe if you're like, okay, I don't get that. What we can do is, why don't we figure out how much hydrogen is produced? I mean, hydrogen, like just, or iron, who cares? I mean, I guess let's go with iron, Fe3O4, the iron oxide, okay? If I have 2.00 moles of H2O and all of it reacts, the ratio is 1-to-4, 1 mole Fe3O4 to 4 moles of H2O, like I am doing Stoich, so I have to use the original mole ratio. I can produce 0.5 moles of Fe3O4. And I don't need to go to mass. Obviously, this can help me get to the next problem because it's asking for mass. Once I figure out which one is which, I just can continue that problem. But what this is saying is 2 moles can, at max, make 0.5 moles of Fe3O4. What about my 2.99 moles of iron? Well, iron would be a ratio of, again, 1 mole of the larger compound, Fe3O4, and 3 moles of Fe. Based on this, essentially, I can make 1 mole of Fe3O4 with this amount. The thing is, water can only make half of that, so therefore, which is my limiting reactant? Again, the water. Whichever one can make less product must be the limiting reactant. So those are two ways to prove, because I would be asking you to prove why it's the lower ratio, or sorry, whether the ratio doesn't match up appropriately. And again, not just say, I'm not going to accept the answer if the ratio doesn't match up. I need to see some sort of you showing me how that's working. Or you just go ahead and do, hey, I'll do a quick mole-to-mole stoichiometry and figure out which one produces less. Again, one might be faster than the other based on how you kind of look at it. Okay? So we got that now. So we know H2O is the limiting reactant. Okay? So that kind of makes the excess reactant. The excess reactant is the other one. The iron is the excess reactant. But I'm not going to really use that at all anymore because the excess reactant won't tell me how much will be produced. There's too much of it. It's going to give me answers higher than it should be. So I have answered part A. This is going to make 0.5 moles of Fe3O4. And then look at what the next question is. What mass in grams of black iron oxide would be produced? Let's just finish this up. 1 mole. And the molar mass of Fe3O4 is 231.55, I think I heard. Yep, grams. All right. And then I could just multiply those together, make sure I use the correct sig figs, and I get 116 grams will be produced. The end. All right. So that does actually lead to that second method, that B method of calculating the moles. You can kind of continue using that to then complete the rest of the problem. If you just look at the ratio, of course, then you don't have to write both of them out, but you're almost doing the same amount of work in the end. Okay, pretty close to it. So 116 grams is how much is produced from the limiting reactant. All right, so what do I do next? I'm going to leave that there. Part B was 116. What's my last thing? What mass in grams of, what mass in grams of excess reactant remains in the reaction? Okay, well, I probably shouldn't have gotten rid of everything, but we'll go ahead and just do it over again. What I need to do here is I need to go from the limiting reactant to the excess reactant. So my limiting reactant again was H2O. I'll just start over. 36.0 grams H2O, 1 mole H2O, 18 grams. And now I'm going to go from moles of water to moles of iron. That's the excess reactants. That's what I mean. I'm trying to solve for how much reactant am I going to use in a mass, from a mass perspective. 1 mole, 55.85 grams. What this then tells me, hopefully with some good math along the way, is that I will use 83.2 grams of iron. I will only use 83.2 grams of iron at the end there. Okay? That's what I'm looking at there. Yep. I'm going to actually double check that just to make sure. I feel something looking at my own work. Sorry, 3 times. 83 point, actually getting 7.8, but that's fine. So around 83 grams of iron is used. That's how much is used. So how much is then remaining in the reaction? 167 minus 83.2. Okay, that would be 8, 6, 3, and then 8. 83.8 grams is left. So I subtract out the original mass that I have and see how much is left. So I essentially use half of it, okay, in the end. So there's a lot of iron left over there, okay? But that's your process. That's what you see there. So let's do one more. Oops, I just got to go like this. All right, let's look at this one. Carbon reacts with steam at high temperatures to produce hydrogen and carbon monoxide. So first off, it doesn't even write the reaction. We should be able to do this. It's carbon reacts with steam. Steam is water, H2O. It will produce carbon dioxide and hydrogen. Okay? I want to balance that chemical reaction. It's actually all balanced. 1 to 1, 2, 2, 1, 1. So everything is 1 to 1. So this one actually should be a lot easier for me to figure out. And look at that. They already give us moles. I have 2.4 moles of carbon and 3.1 moles of water. Well, what's my ratio telling me here? It's 1 to 1. I need, for every mole of carbon, I need 1 mole of water in order for it to completely react. I'm a little bit short on the carbon, okay? So carbon is going to be my limiting reactant. That's going to be my limiting reactant. If you're still sitting there going, wait, how, like, let me use the other method real fast. And again, this is really nice because they just start us off with moles. Okay, but carbon is my limiting reactant. Water is going to be my excess reactant, or steam. And I could go ahead and solve for, what am I going to be having to solve for? It wants me to solve for H product, so I can pick one. Let's just start with carbon monoxide, and it only wants me to do moles. Well, it's 1 mole of carbon monoxide and 1 mole of carbon. So this is only going to produce 2.4 moles of carbon monoxide. I don't think I really need to do the other calculation. All I would do is put 3.1 moles of H2O in, and it's still a 1-to-1 ratio. Clearly, carbon produces less carbon monoxide, less products. So we're going to get 2.4 moles of carbon monoxide. I mean, I'll show it for you, but I'm hoping you can kind of see it. How much H2 should form? Well, guess what? Since it's a 1-to-1 ratio, it's going to be also 2.4 moles of H2. Again, technically 2.40 moles of H2. All right. After that, it says what's the mass of each product. So then you could just continue this on. 1 mole, basically 28.01 grams. 2 grams of H2 for 1 mole. So you're going to get 80 grams of hydrogen. And you're going to get 67.2 grams of carbon monoxide. Around that, maybe a little bit different, but 67.2 grams of carbon monoxide. All right. So again, use the ratio, use the, find one of the products, see which one produces less, and that's your limiting reactant, and go from there. I will go ahead and quickly add in here. Let's do the last part again. Let's find the excess amount of moles, because it doesn't actually give me a mass, so I can't subtract that. How many moles of water would be left over? Well, once again, I would do 2.4 moles of carbon, and I'm going to go to water, 1 mole of water, 1 mole of carbon. I'm using 2.4 moles. I guess I could figure out how much mass would still be there. I would use 2.4 moles of water. 3.10 minus 2.40 equals 0.7 moles of 2.70 moles of water remains. Okay, so that shows the excess reactant calculation. So it's just this stoichiometry. I mean, this is huge in order to be able to put everything together. This ultimately is how we do the chemical reactions in a laboratory. If we're trying to produce a particular amount of medicine, where we know what the limiting reactant is going to be, we understand the percent yield of the reaction, and we can put all of those things together to hopefully produce exactly how much I'm expecting in the end. All right, so great technique, and if you need any help, just you go from there. All right, thank you.